Hello, in this lecture we'll answer two questions. In the first question we'll find out the area of this circle that is inside square ABCD, and in the second question we'll find out the value of the green area that is inside a quarter circle. So we'll start with the first question. In the drawing we have square ABCD. Inside square ABCD we have a circle. We know that angle TBC equals to 30 degrees, line segment PD equals to 5 units, and our mission is to find out the area of this circle that is inside square ABCD. So first of all, we will define the center of this circle as O. We will join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself. Therefore, OP is the radius of the circle that we will define as R. And we have the radius OP that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle will be equal to 90 degrees. Likewise, we join points O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is also the radius of the circle that is equal to R. And again, we have the radius OQ that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. We know that all the angles inside square ABCD are right angles, that is to say, this angle, it is a right angle, it is equal to 90 degrees. This is also a right angle that is equal to 90 degrees. This angle is also equals to 90 degrees, and finally this angle is the right angle, it is equal to 90 degrees. Okay, so inside quadrilateral AQPO we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees plus the size of the fourth angle. In total they must be equal to 360 degrees. Therefore this fourth angle must be also equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So 270 degrees plus 90 degrees is 360 degrees. Okay, so I found out that inside quadrilateral AQPO we have 4 right angles, therefore quadrilateral AQPO is a rectangle. So I write it down. Quadrilateral AQPO is a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, AQ equals to PO. AQ equals to PO, but we have already found out that PO equals to R. So I can write here that PO equals to R. And from this equation, AQ equals to PO equals to R, we will derive that AQ is also equals to R. Here you can write down that AQ equals to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that AP equals to QO. AP equals to QO, but we have already found out that QO equals to R. And from this equation, AP equals to QO equals to R, we will derive that AP is also equals to R. AP equals to R. Here we found out that AP equals to R. So we actually found out that quadrilateral AQPO is not a rectangle but a square because of the fact that all of its sides are equal to each other, they are equal to R. So quadrilateral AQPO is a square. We know that all the sides of square ABCD are equal to each other. That is to say, side AD equals to side AB. In square ABCD, side AD equals to side AB. What is the length of side AD? AD equals to 5 plus R, and it is equal to AB. What is the length of side AB? AB equals to R plus QB. So in conclusion, we found out that 5 plus R equals to R plus QB. Here we subtract R from this equation, and we get that 5 equals to QB, or QB equals to 5 units. QB equals to 5 units. In the next step, I will present to you rule number 2, and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common extreme point to a circle are equal. Here we have the common extreme point P. From the common extreme point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. We can actually implement rule number 2 in our drawing. Why? Because in our drawing, if we focus on the common extreme point B, from the common extreme point B, we have two tangents to this circle, tangent BQ and tangent BS. And according to rule number 2, they are equal to each other. That is to say, BQ equals to BS. But we have already found out that BQ equals to 5 units. So we can write here that BQ equals to 5. And from this equation, 5 equals to BQ equals to BS. We will derive that BS is also equals to 5 units. BS equals to 5 units. Here, BS equals to 5 units. In the next step, we will join points Q and S together by a straight line. When joining points Q and S together, we created here triangle QBS. In triangle QBS, side BS equals to side BQ. They are both equal to 5 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. That is to say, in front of those two equal sides or equal angles, that is to say, those two angles that are located in front of equal sides must be equal to each other. So, if this angle equals to alpha, then this angle must be also equal to alpha because of the fact that those two angles that are located in front of equal sides must be equal to each other. So both those two angles are equal to alpha. What is the size of this angle? Angle QBS. Angle QBS will be equal to the big angle, that is angle ABC, minus this angle, that is angle TBC. Angle ABC minus angle TBC equals to the size of this angle. That is to say, angle, the missing angle, angle ABT, this angle, will be equal to angle ABC, that is 90 degrees, minus angle TBC, that is 30 degrees. 90 degrees minus 30 degrees, it is 60 degrees. So I found out that angle, this angle QBS equals to 60 degrees. So, what is the sum of those two angles? The sum of those two angles will be equal to 180 degrees minus this angle. So 180 degrees minus 60 degrees is the sum of those two angles. That is to say, 180 degrees minus 60 degrees is 120 degrees. So alpha plus alpha equals to 120 degrees. So I write it down. I found out that alpha plus alpha equals to 120 degrees in triangle QBS. So alpha plus alpha is to alpha, that is equal to 120 degrees. Here we will divide this equation by 2 and we get that angle alpha equals to 180 degrees, 120 degrees over 2 is 60 degrees. So I actually found out that this angle alpha equals to 60 degrees. And this is also angle alpha that is equal to 60 degrees. So actually, in this triangle QBS, we have three angles that are all equal to 60 degrees. Therefore, this triangle QBS is an equilateral triangle. So I write it down, triangle QBS is an equilateral triangle because of the fact that all of its angles are equal to 60 degrees. And we know that all the angles of an equilateral triangle, all the sides of an equilateral triangle are equal to each other. So, side in the equilateral triangle QBS, side QB equals to 5 units, side QS also equals to 5 units. Therefore, the missing side QS must be also equal to 5 units. QS equals to 5 units. In the next step, we join points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of this circle that is equal to R. We have the radius OS that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. So in the next step, I will copy quadrilateral OSBQ in a new page and we'll analyze quadrilateral OSBQ. Okay. Angle OQB equals to 90 degrees, this angle, and angle OSB also equals to 90 degrees. Angle QBS equals to 60 degrees, this angle. So actually, this is quadrilateral QBOS that I copied from the original drawing. In quadrilateral QBOS, we have two right angles, and this angle equals to 60 degrees. Angle QOS is the missing angle. What is the value of angle QOS? We know that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, 360 degrees minus the sum of three other angles must be equal to the size of the missing angle. So the missing angle here, angle QOS, will be equal to 360 degrees minus the sum of those three angles, that is to say, it will be equal to minus the sum of this angle, that is 90 degrees, plus 90 degrees, plus 60 degrees. So the missing angle QOS will be equal to 360 degrees minus 90 degrees plus 90 degrees is 180 degrees. 180 degrees plus 60 degrees is 240 degrees. So we found out that the size of the missing angle is 360 degrees minus 240 degrees, that is 120 degrees. So this angle equals to 120 degrees. Okay, here, the missing angle QOS equals to 120 degrees. So I can write here that this is the missing angle QOS, that is equal to 120 degrees. In the next step, I will present to you the law of cosines, and we'll implement the law of cosines in the green triangle QOS. This green triangle QOS. So what is the law of cosines? The law of cosines is true in any triangle. So if we have triangle ABC, that could be any triangle. This is triangle ABC. the length of side AB equals to A units, side AC equals to B units in its length, and finally side BC equals to C units in its length, and the angle between side AB and side AC is theta. So here, according to the law of cosines, in this triangle ABC, we will get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I'll repeat again. In this triangle ABC, that could be any triangle, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Now we will implement this law, the law of cosines, in the green triangle QOS. So I'll copy triangle QOS in this new page and we'll implement the law of cosines in this triangle. So actually, this is triangle QOS that I copied from the original drawing. QO equals to 1, OS equals to 1, QS equals to 5 units, and this angle QOS equals to 120 degrees. So according to the law of cosines, we will get that 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. Again, 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. 5 squared is 25, and it is equal to R squared plus R squared is 2R squared, minus 2 times R is minus 2R squared, times cosine 120 degrees. Cosine 120 degrees equals to minus 1R. So here we have 2 in the numerator and 2 in the denominator, 2 in the numerator and 2 in the denominator, so 2 will get cancelled. And here minus times minus is plus. So in conclusion, found out that 25 equals to 2R squared, and this expression in total equals to plus R squared. So here we found out that 25 equals to 2R squared plus R squared is 3R squared. Here we will divide this equation by 3, and we get that R squared equals to 25 over 3. And what is the area of our circle? The area of our circle, the area of any circle, is equal to pi r squared. In our specific circle, the area is also pi r squared, and we already found out that r squared equals to 25 over 3, so here we substitute r squared in this equation by 25 over 3, and we get that the area of our circle equals to pi, and r squared is 25 over 3. So in conclusion, we found out that the area of our circle equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. Okay, so we finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question in 3 different methods. So here in the drawing we have a quarter circle. Inside this quarter circle we have a small circle. We know that line segment CD equals to 8 units, and this angle ACD equals to 90 degrees, and our mission is to find out the value of this green shape. We start with the first method, and we define the center of the small circle as J. We define the point of tendency CD with the small circle as E. We define the point of tendency of tangent OB with this circle as F. The next step, we join points J and E together by a straight line. Point J is the center of the small circle, point E is the point of the small circle itself, therefore JE is the radius of this circle that we define as R. And we have the radius JE that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Likewise, we join points J and F together by a straight line. Point J is the center of the circle, point F is the point of the circle itself, therefore JF is the radius of this small circle that is equal to R. And again, we have the radius JF that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. And because of the fact that AOB, this shape AOB is a quarter circle, it means that point O is the center of the quarter circle. This angle equals to 90 degrees, and OA is the radius of the quarter of the circle that we will define as capital R. So AO as a radius of the quarter circle must be a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of AO at point C? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, this missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of AO at point C to 180 degrees. This angle must be also equal to 90 degrees. So here, from the center of this circle, of the small circle, that is to say from point J, we will go perpendicular on CO. Here from point J, we go perpendicular on CO. So this angle equals to 90 degrees, and this angle it is also equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO as T. So inside quadrilateral CETJ, this quadrilateral, we have 1, 2, 3 right angles, and therefore the fourth angle must be also equal to 90 degrees. Likewise, inside quadrilateral TJOF, we have 1, 2, 3 right angles, therefore this fourth angle must be also equal to 90 degrees. So we actually found out that this angle EJF equals to 90 degrees plus 90 degrees, that is 180 degrees. Angle EJF equals to 180 degrees, therefore angle EJF is a straight line. If angle EJF is a straight line, it means that line segment EJF is a straight line, and if line segment EJF is a straight line, it means that EF is also a straight line. Line segment EF is also a straight line. And if EF is a straight line, it means that quadrilateral CEOF, this quadrilateral, is a rectangle. I write it down. Quadrilateral CEOF is a rectangle. Why? Because it has 4 right angles. Quadrilateral CEOF has 4 right angles, therefore it is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF. CO equals to EF. But we have already found out that EF equals to R plus R, that is 2R. And for this equation, CO equals to EF equals to 2R. And we derive that CO is also equal to 2R. CO equals to 2R. Here, CO equals to 2R. Okay. So in the next step, we will join points O and D together by straight line. Point O is the center of the quarter circle, point D is the point on the quarter circle itself, therefore OD is the radius of this quarter circle, that is equal to capital R. In the next step, we will implement the Pythagoras theorem. On the green right triangle, triangle COD. The green right triangle, triangle COD by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle COD is OD, therefore the square of the hypotenuse is OD squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to CO squared plus CD squared. Repeat again. In the right plane triangle, triangle COD, according to the Pythagoras theorem, OD squared equals to CO squared plus CD squared. OD equals to capital R, therefore OD squared is capital R squared. That is equal to CO squared. CO equals to 2R. Of course, here square is 2r squared, that is 4r squared, plus CD squared. CD equals to 8 units according to what is given as the equation. Of course, CD squared is 8 squared, that is 64. So in conclusion, we found out that according to equation number 1, capital R squared equals to 4r squared plus 64. Here we subtract 4r squared for this equation number 1, and we get that according to equation number 1, capital R squared minus 4r squared equals to 64. Found out that according to equation number 1, capital R squared minus 4r squared equals to 64. But what is actually the area of the green shape? From the drawing, it is very easy to see that the area of the green shape is equal to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. So, what is the area of the quarter circle? The area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle. The area of the small circle is pi R square. Okay. So you take here pi over 4 as a common factor out of those two expressions. So what is left from pi times capital R square over 4 after we took home it pi over 4 as a common factor? What is left is actually capital R square. And what is left from minus pi R square after we took home it pi over 4 as a common factor? What is left is actually minus 4 times R square. Okay, so why? Because minus 4 times R square times pi over 4 equals to exactly to minus pi R square. So here we have capital R square minus 4 R square, but we have already found out that according to equation number 1, capital R square minus 4 R square equals to 64. Therefore we can substitute capital R square minus 4 R square by 64. We'll do it now. We'll get that this expression in total equals to pi over 4 times 64. Here 64 over 4 is 16, so this expression in total equals to 16 pi. So we found out that the area of this green shape equals to exactly to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. So we finished with the first method. In the next step I will present to you how to find out the area of this green shape according to the second method. In the second method we follow the fields that we already found out in the first method. We have already found out that CO equals to 2R, AO equals to capital R, this angle equals to 90 degrees, this is the radius of the small circle, this angle it is also equal to 90 degrees. So what is the value of line segment AC. From the drawing, it is very easy to see that AC equals to AO minus CO. Again, AO minus CO equals to AC. AO minus CO. That is to say, AC equals to AO, that is capital R, the radius of the quarter circle, minus CO. CO equals to 2R. So in conclusion, we found out that AC equals to capital R minus 2R. Okay, so in the next step, we'll complete the quarter circle to a circle. So we completed the quarter circle to a circle. Then we will extend the radius AO by a straight line until it touches the circle. We will define the touching point of the extended radius AO in the circle as T. So here point O is the center of the big circle, point T is the point of the big circle itself, therefore OT is the radius of the big circle that is equal to capital R. In the next step, we will extend the straight line DC by a straight line until it touches the circle. We'll define the touching point of the extended straight line DC in the circle as point M. We'll join points O and M together by a straight line. Point O is the center of the big circle, point M is the point of the big circle itself, therefore OM is the radius of the big circle that is equal to capital R. Likewise, we join points O and D together by a straight line. Point O is the center of the big circle, point D is the point of the big circle itself, therefore OD is the radius of the big circle that is equal to capital R. Here we extended the straight line DC by straight line. When you extend a straight line by straight line, the result must be a straight line. So the result that is DM must be a straight line. So if we focus on the lower side of the straight line DM at point C. Here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the lower side of MD at point C? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees according to rule number 3. Therefore the missing angle here must be equal to 90 degrees in order to complete the sum of the angles at the lower side of MD at point C to 180 degrees. This angle must be equal to 90 degrees. So we found out that we have here two right triangles, triangle MCD and the right triangle, triangle CDO. We'll prove that those two right triangles can go into each other. So I write it down. We'll prove that the right triangle, triangle MCO can go into the right triangle, triangle CDO. So why those two right triangles can go into each other? First of all, those two right triangles have a common side. CO is a common side that belongs to both triangles. So CO equals to itself. It's a common side that belongs to both triangles. In addition, MO equals to OD. They are both the radii of the big circle, therefore they are equal to each other. Okay. So we proved that the perpendicular and the hypotenuse in those two right triangles congruent, and it is enough in order to prove that those two right triangles can go into each other. I will explain you why. So if, for example, we have two right triangles that can go into each other by their hypotenuse and one perpendicular, this is the right triangle, triangle ABC. The hypotenuse AC equals to 5 units and the perpendicular AB equals to 4 units. And we also have right triangle DEF. The hypotenuse DF is also equals to 5 units and the perpendicular BO is also equals to 4 units. So those two right triangles have the hypotenuse and the perpendicular that congruent. Therefore, the third side, that is to say BC in this right triangle and EF in this right triangle, must also congruent. Why? Because BC, what is the length of BC? According to the Pythagoras theorem, the length of side BC will be equal to the square root of 5 square minus 4 square. 5 square is 25, 4 square is 16, 25 minus 16 is 9, and the square root of 9 is 3. Here also EF will be equal to the square root of 5 square minus 4 square, that is 3. So we found out that if we have two right triangles with hypotenuse and one perpendicular that congruent, then the third side must also congruent. Okay, here the third side in both those two right triangles is equal to 3 units. Okay, according to the Pythagoras theorem. So here we proved that one perpendicular and the hypotenuse of those two right triangles congruent, therefore the third side was also congruent, and therefore those two right triangles can point to each other according to side rule. So I write it down. Triangle MCO can point to triangle CDO according to side rule. They have from the beginning two sides that can point. Here the hypotenuse and one perpendicular, and the third side must also can point in those two right triangles according to the Pythagoras theorem. Therefore, those two right triangles can point to each other according to side rule. And from the fact that those two right triangles can point to each other, we will derive that side DC in the green right triangle equals to side CM in this CMO right triangle. So DC equals to CM. DC equals to CM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can point to each other, therefore the corresponding sides, that is to say DC and CM, must also congruent. But according to what is given as the equation, DC equals to 8. And for this equation, 8 equals to DC equals to CM, we derive that CM is also equals to 8 units. CM equals to 8 units. Okay, here CM equals to 8 units. So in the next step, I will present to you rule number 11, and we will implement rule number 11 in our drawing. According to rule number 11, if we have chord AB that intersects with chord CD at point O, again chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing. Why? Because in our drawing we have chord AT that intersects with chord MD at point C. Again, chord AT intersects with chord AMD at point C. So I write it down in our drawing. We have chord AT intersects with chord MD at point C. Point C is the intersection point. I'll put it again. Chord 18 intersects with chord MD at point C. Okay, therefore, according to rule number 11, we get that MC times CD equals to AC times CT. Again, MC times CD equals to AC times CT. MC times CD equals to AC times CT. I'll repeat again. MC times CD equals to AC times CT. MC equals to 8, CD equals to 8, MC times CD is 8 times 8, that is 64, and it is equal to AC. AC is capital R minus 2R, and what is the value of CT? Here CT equals to 2R plus capital R. So in conclusion, we found out that according to rule number 11, 64 equals to capital R minus 2R times capital R plus 2R. Or 64 equals to capital R plus 2R times capital R minus 2R. Okay, what is the value of this expression? According to the algebraic identity that A plus B times A minus B equals to A squared minus B squared, in our specific expression, A equals to capital R and B equals to 2R. Therefore, A squared is capital R squared because A equals to R minus B squared. B is 2R, so minus B squared is minus 2R squared. In conclusion, we found out that 64 equals to capital R squared minus 2R squared. That is to say, 64 equals to capital R squared minus 2R squared is minus 4R squared. Repeat again, we found out that 64 equals to capital R squared minus 4R squared. Okay, but what is the area of the green shape? The area of the green shape is equal to the area of the quarter circle minus the area of the small circle. I'll repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R squared over 4 minus the area of the small circle, that is pi R squared. Here we took pi over 4 as a common factor out of those two expressions, and inside the brackets we left only with capital R squared minus 4R squared. But we have already found out that capital R squared minus 4R squared equals to 64. So we can substitute capital R squared minus 4R squared here by 64, and we get that this expression in total will be equal to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Okay, so we finish with the second method. In the next step I present to you how to find out the area of this green shape according to the third method. We have already found out that CO equals to 2R, AO equals to capital R. It is the radius of the quarter circle. We have already found out that AC equals to capital R minus 2R. This angle equals to 90 degrees. And this angle, it is also equal to 90 degrees. This is the radius of the small circle. In the next step, we will complete the quarter circle to a semicircle. We'll extend the radius AO until it touches the semicircle. We extended the radius AO by a straight line until it touches the circle. We define the touching point of the extended radius AO at the semicircle as T. So point O is the center of the semicircle. Point T is the point on the semicircle itself. Therefore, OT is the radius of the semicircle that is equal to capital R. Okay. So here we extended the radius AO, that is a straight line, by a straight line. When you extend a straight line by a straight line, the result is a straight line. So AT is a straight line. AT is a straight line. Therefore, we can see AT as a chord. So we have chord AT that passes through the center of the semicircle. Any chord that passes through the center of the semicircle must be the diameter of the semicircle. So here AT, chord AT that passes through the center of the semicircle is the diameter of the semicircle. In addition, we know also that AT it is equal to capital R plus capital R, that is 2 times capital R. That is another reason that AT is the diameter of the semicircle. So AT is the diameter of the semicircle, and we join points C and D together by a straight line. We join points A and D together by a straight line. We created there peripheral angle ADT. This peripheral angle ADT rests on AT, that is the diameter of the semicircle, and we have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of the circle or semicircle must be equal to 90 degrees. So we have peripheral angle A and B. This is a peripheral angle that rests on AB, that is the diameter of the circle. Therefore, peripheral angle A and B equals to 90 degrees. We can implement rule number 5 in our drawing, because in our drawing we have peripheral angle ADT that rests on AT, this is the diameter of this circle. Therefore, peripheral angle ADT will be equal to 90 degrees according to rule number 5. We define angle ATD as alpha and angle TAD as beta. We'll focus on the right triangle, triangle ADT. In the right triangle, triangle ADT, this angle equals to 90 degrees. Therefore, the sum of the two other angles must be also equal to 90 degrees. Why? Because 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in a triangle. That is to say, alpha plus beta must be equal to 90 degrees. Here we subtract alpha from this equation and we get that beta equals to 90 degrees minus alpha. Then we subtract beta from this equation and we get that alpha equals to 90 degrees minus beta. We'll focus on the right green triangle, triangle ACD. In the right green triangle, triangle ACD, this angle equals to beta. This angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So this angle must be equal to 90 degrees minus beta. But we have only found out that 90 degrees minus beta equals to alpha. So you can write here that this angle equals to alpha. Likewise, we focus on the right triangle, triangle DCT. In this right triangle DCT, this angle equals to alpha, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to beta, therefore this angle will be equal to beta. In the next step, we'll prove that the right green triangle, triangle ACD, is similar to the right green triangle, triangle CDT. Those two right triangles are similar to each other. So I write it down. Triangle ACD is similar to triangle CDT. The right triangle, triangle CDT. So why those two right triangles are similar to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So here angle ADC is equal to this angle. This is actually angle CTD. In addition, those two angles, they are both equal to beta, therefore they are equal to each other. So this angle is angle CAD. It is equal to this angle is actually angle CDT. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this angle is angle ACD. That is equal to this angle, it is actually angle DCT. So actually prove that those two right triangles are similar to each other according to angle similarity rule. So I write it down, triangle ACD is similar to triangle CDT according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that AC in the right triangle ACD over CD in the right triangle CDT equals to CD in the right triangle ACD over CT in the right triangle CDT. I repeat again, we conclude that AC over CD equals to CD over CT. AC is capital R minus 2R over CD, CD is 8. What is the value of CT? CT equals to 2R plus capital R. In conclusion, we found out that according to equation number 1, capital R minus 2R over 8 equals to 8 over capital R plus 2R. We will cross multiply this equation number 1, and we get that according to equation number 1, 8 times 8 is 64, that is equal to capital R plus 2R times capital R minus 2R. So 64 equals to, we already found out that capital R plus 2R times capital R minus 2R equals to capital R squared minus 4R squared. So according to equation number 1, we found out that 64 equals to capital R squared minus 4R squared. But what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Okay. Repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We already found out that the area of the quarter circle equals to pi times capital R squared over 4, and the area of the small circle equals to pi R squared. Here we took pi over 4 as a common factor out of those two expressions. Inside the brackets we left with capital R squared minus 4R squared. And we already found out that capital R squared minus 4R squared equals to 64. Therefore we can substitute capital R squared minus 4R squared in this equation by 64. We'll do it now, and we get that here pi over 4 times 64. So this expression in total equals to pi over 4 times 64. 64 over 4 is 16. So this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units. So in terms of numbers, it is equal to 50.265 square units. Okay, we finished with the second question. In the next step, I'll summarize the lecture. We start with the first question, of course. the drawing, we have square ABCD. Inside square ABCD, we have a circle. We know that angle CBT equals to 30 degrees, line segment PD equals to 5 units, and our mission is to find out the area of this circle. So we define the center of this circle as O. Here we have the radius OQ that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We have the radius OP that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We know that all the angles inside square ABCD are right angles, so all those 4 angles are right angles. So inside quadrangle AQPO, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So inside quadrangle AQPO, we have 4 right angles. Therefore, quadrangle AQPO is a rectangle. You know that the opposite sides of a rectangle are equal to each other. That is to say, AQ equals to PO. But we have already found out that PO equals to R. And for this equation, AQ equals to PO equals to R, we have derived that AQ is also equals to R. Here, AQ is also equals to R. Likewise, according to the sum that the opposite sides of a rectangle are equal to each other, we get that AP equals to QO. But we have already found out that QO equals to R. And for this equation, AP equals to QO equals to R, we derive that AP is also equals to R. Here, AP is also equals to R. So we found out that quadrangle AQPO is a square and not a rectangle. Why? Because all of its sides are equal to each other, they are equal to R. Then we know that all the sides of a square ABCD are equal to each other. That is to say, side AB equals to side AD. Or AD equals to AB square ABCD. What is the value of AD? The length of side AD is R plus 5. The length of side AB is R plus QB. So in conclusion, we found out that 5 plus R equals to R plus QB. We subtracted R from this equation and we found out that QB equals to 5. Here, QB equals to 5 units. Then I presented to you rule number 2 and we implemented rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. Here, from the common external point P, we have tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. We can implement rule number 2 in our drawing, because in our drawing we have the common external point B. From the common external point B, we have tangent PQ and tangent BS to this circle. And according to rule number 2, BQ equals to BS. I repeat again, BQ equals to BS according to rule number 2. But we have already found out that BQ equals to 5. And from this equation, 5 equals to BQ equals to BS, we derive that BS is also equals to 5. Here, BS is also equals to 5. Okay, then we join points Q and S together by a straight line. In this way, we created here triangle QBS. What is the size of this angle? The size of this angle is equal to the size of the big angle ABC that is equal to 90 degrees minus the size of this angle DBC that is equal to 30 degrees. So 90 degrees minus 30 degrees, it is 60 degrees. So this angle equals to 60 degrees. Okay. So inside triangle QBS, those two sides are both equal to 5 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if this angle is equal to alpha, then this angle must be also equal to alpha because of the fact that they are located in front of equal sides, they are equal to each other. So those two angles, they are both equal to alpha. What is the sum of those two angles? The sum of those two angles must be equal to 180 degrees and 60 degrees, that is 120 degrees. That is to say, alpha plus alpha must be equal to 120 degrees. Alpha plus alpha is 2 alpha, so 2 alpha equals to 20 degrees. We divided this equation by 2 and found out that angle alpha equals to 60 degrees. So those two angles are both equal to 60 degrees. So inside triangle QBS we have all angles are equal to 60 degrees, therefore triangle QBS is an equilateral triangle. And we know that all the sides of an equilateral triangle are equal to each other. That is to say QB equals to BS equals to 5 units. So therefore QS must be also equal to 5 units. Okay? Then we join point O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of this circle that is drawn to the point of tendency, therefore according to rule number 1 this angle equals to 90 degrees and this angle equals also to 90 degrees. Then I copied quadrilateral QBOS in a new page and we analyze quadrilateral QBOS. This is quadrilateral QBOS that I copied from the original drawing. Those two angles are both equal to 90 degrees, this angle equals to 60 degrees, and this is the missing angle. Angle QOS is the missing angle. What is the size of the missing angle? The size of the missing angle equals to the sum of the angles in this quadrilateral, that is 360 degrees, minus the sum of those three angles. That is to say, the size of the missing angle will be equal to 360 degrees minus 90 degrees plus 90 degrees plus 60 degrees, that is 240 degrees. So in conclusion, we found out that the size of the missing angle equals to 360 degrees minus 240 degrees, that is 120 degrees. So this missing angle equals to 120 degrees in its size. So you can I tell that this the missing angle, angle QOS, equals to 120 degrees. Then I presented to you the law of cosines and we implemented the law of cosines in this green triangle, triangle QOS. What is the law of cosines? The law of cosines is true in any triangle. So if we have here triangle ABC that could be any triangle, the length of side AB is A units, the length of side AC is B units, and side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. We can implement the law of cosines in any triangle, and especially in this triangle, triangle QOS. So we implemented the law of cosines in this triangle, triangle QOS. According to the law of cosines, we will get that 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. Again, 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. 5 squared is 25. That is equal to R squared plus R squared is 2R squared minus 2 times R is minus 2R squared. Cosine 120 degrees equals to minus half to minus 1 half. Therefore, substitute cosine 120 degrees by minus 1 half. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus. So in total, this expression equals to plus R squared. So we found out that 25 equals to 2R squared plus R squared, that is 3R squared. So 25 equals to 3R squared, we divided this equation by 3 and found out that R squared equals to 25 over 3. And we know that the area of our circle is pi R squared, but we have already found out that R squared equals to 25 over 3, so we can substitute R squared by 25 over 3, we did it, and we got that the area of our circle is 25 pi and 25 pi times R squared. R squared is 25 over 3. That is to say, the area of our circle equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. Okay, we finished with the first question, then I presented to you the second question, and we solved the second question in 3 different methods. So in the drawing we have a quarter circle. Inside this quarter circle we have a small circle. Line segment CD equals to 8 units, angle ACD equals to 90 degrees, and our mission is to find out the value of the area of the green shape. Okay, or the size of the area of the green shape. So first of all we started with the first method. We define the center of the small circle as J. We have the radius JE that is drawn to the point of tendency, therefore this angle equals to 90 degrees according to rule number 1. We have the radius JF that is drawn to the point of tendency, therefore this angle equals to 90 degrees according to rule number 1. We know that AOB is a quarter circle, therefore point O is the center of the quarter circle, this angle equals to 90 degrees. And AO is the radius of the quarter circle that is equal to capital R according to our definition. So AO is the radius of the quarter circle, that is, therefore it is absolutely a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have here? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees. So the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of AO at point C to 180 degrees. This angle must be also equal to 90 degrees. Okay, so from point J, that is the center of the small circle, we draw perpendicular on CO. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO as T. So in quadrilateral CE TJ we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. In quadrilateral TJOF we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So angle EJF, this angle equals to 90 degrees plus 90 degrees, it is 180 degrees. Therefore angle EJF that is equal to 180 degrees, it is a straight line. If therefore EJF is also a straight line, and therefore EJ is also a straight line. EJF is a straight line, therefore EF is also a straight line. Line segment EF is a straight line, and if line segment EF is a straight line, it means that quadrilateral CEOF is a rectangle. Why? Because quadrilateral CEOF has 4 right angles. Therefore it is a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say CO equals to EF. But we have already found out that EF equals to R plus R, that is to R. And from this equation CO equals to EF equals to 2R, we derive that CO is also equals to 2R. Here CO equals to 2R. Then we join points O and D together by a straight line. Point O is the center of the quarter circle, point D is the point of the quarter circle itself, therefore OD is the radius of the quarter circle that is equal to capital R. Then we implemented the Pythagoras theorem on the right green triangle, triangle COD. According to the Pythagoras theorem on the right green triangle, triangle COD, OD square equals to CO square plus CD square. Again, OD square equals to CO square plus CD square. OD equals to capital R, therefore OD square is capital R square. CO equals to 2R, therefore CO square is 4R square. CD equals to 8, therefore CD square is 8 squared, that is 64. So in conclusion, we found out that capital R square equals to 4R square plus 64. We subtracted 4R square from this equation and found out that according to equation number 1, capital R square minus 4R square equals to 64. What is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. And the area of, so here, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to pi times capital R square over 4. The area of the small circle equals to pi times R square. Then we took pi over 4 as a count factor of those two expressions. What is left from pi times capital R square over 4 after we took from it pi over 4 as a count factor? What is left is actually capital R square. What is left from minus pi R square after we took from it pi over 4 as a constant factor, what is left is actually minus 4r squared. Why? Because minus 4r squared times pi over 4 equals to minus pi r squared. So here we have capital R squared minus 4r squared, but we have already found out that capital R squared minus 4r squared equals to 64. Therefore, we can substitute capital R squared minus 4r squared by 64. We did it, and we got that this expression in total equals to pi over 4 times 64. 64 over 4 is 16, so this expression in total equals to 16 pi. So we found out that the area of the ring shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the first method, then I presented to you how to find out the area of the ring shape according to the second method. In the second method, we used all the things that we already found out in the first method. We have already found out that OC equals to 2R, AO is equal to capital R. What is the value of AC? The value of AC is AO minus CO. Again, AC equals to AO minus CO. So AC equals to AO, that is capital R, minus CO, that is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. We have already found out that this angle equals to 90 degrees in the first method, and this angle equals to 90 degrees because it is a quarter circle. Here, AOB is a quarter circle. Then we completed the quarter circle to a circle. We extended the radius AO by straight line until it touches the circle at point T. Point O is the center of the big circle. Point T is the point of the big circle itself. Therefore, OT is the radius of the big circle that is equal to capital R. Then we extended the straight line DC by straight line until it touches the circle at point M. When you extend the straight line by straight line, the result must be a straight line. Therefore, DM must be a straight line. If you focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have here? We have this angle that is equal to 90 degrees plus this missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees. In order to complete the sum of the angles on the lower side of MD at point C to 180 degrees, this angle must be also equal to 90 degrees. So we have here two right triangles, triangle ODC and triangle OMC. We proved that those two right triangles can go into each other. Why they can go into each other? First of all, they have a common side CO that belongs to both triangles, so CO equals to itself. And we have DO equals to OM, they are both the radii of the big circle, therefore they are equal to each other. So I repeat again, we found out that CO equals to itself as a common side, and MO equals to OD, they are both the radii of the big circle, therefore they are equal to each other. By proving that the hypotenuse and one perpendicular on those two right triangles congruent, we actually proved that those two right triangles can go into each other according to side rule. Why? Because if, for example, we have two right triangles that can go into each other by their hypotenuse and perpendicular, here AC equals to DF equals to 5 units, and AB equals to DE equals to 4 units. So those two right triangles can go into each other by their hypotenuse and one perpendicular. Therefore, the third side must also congruent. The third side must also congruent. According to the Pythagoras theorem, the value of the third side must be equal to the square root of 5 units minus square root of 4 units, that is 3. So you can see here that the third side in both those two right triangles is equal to 3 units. So we found out that if the hypotenuse and one perpendicular in two right triangles congruent, then the third side must also congruent. Therefore, when we have the hypotenuse and one perpendicular in those two right triangles that congruent, then the third side must also congruent, and therefore we can say that those two right triangles can go into each other according to side rule. Okay? And from the fact that they can go into each other, we derive that DC equals to CM. DC equals to CM according to the rule that corresponding sides of congruent triangles are equal to each other. Those two targets can point to each other, therefore the corresponding side DC and CM must be also equal to each other. But DC equals to 8 units according to what is given as the equation, and for this equation, 8 equals to DC equals to CM, we derive that CM is also equals to 8 units. Here CM equals to 8 units. Then I presented to you rule number 11, and we implemented rule number 11 in our drawing. According to rule number 11, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing. Why? Because in our drawing we have chord AT that intersects with chord MD at point C. Again, chord AT intersects with chord MD at point C. I repeat again. Chord AT intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. Again, MC times CD equals to AC times CT. I'll repeat again. According to rule number 11, we get that MC times CD equals to AC times CT. MC is 8, CD is 8, so MC times CD is 8 times 8, that is 64. AC is R times, AC is capital R minus 2R. CT is capital R plus 2R. So we concluded and found out that 64 equals to capital R plus 2R times capital R minus 2R. And here, according to the algebraic identity that A plus B times A minus B equals to A squared minus B squared, this expression will be equal to A squared minus B squared. And here A will be equal to capital R, B will be equal to 2R. A squared is capital R squared, minus B squared is minus 2R squared. So in conclusion, we found out that 64 equals to capital R squared minus 2R squared. That is to say, 64 equals to capital R squared minus 2R squared is 4R squared. So in conclusion, we found out that capital R squared, 64 equals to capital R squared minus 4R squared. And what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle is pi times capital R squared over 4 minus the area of the circle, that is pi R squared. We took pi over 4 as a common factor out of those two expressions, so inside the brackets we left only with capital R squared minus 4R squared. But we have already found out that capital R squared minus 4R squared equals to 64, so we can substitute capital R squared minus 4R squared here by 64. We did it and we got that this expression in total equals to capital pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers it is equal to 50.265 square units. We finish with the second method. Then I presented to you how to find out the area of the green shape according to the third method. We already found out that CO equals to 2R, AO equals to capital R, here AO equals to capital R is the radius of the quarter circle. We have already found out that AC equals to capital R minus 2R. We have already found out that this angle equals to 90 degrees, this angle also equals to 90 degrees. Then we completed the quarter circle to a semicircle. We extended the radius AO by a straight line until it touches the semicircle at point T. So point O is the center of the semicircle, point T is the point of the semicircle itself. Therefore, OT is the radius of the semicircle that is equal to capital R. We extended the radius AO, that is a straight line, by a straight line. When we extend the straight line by a straight line, the result must be a straight line. So AT is a straight line. If AT is a straight line, we can see AT is chord inside the semicircle. Chord AT passes through the center of the semicircle, that is to say it is passes through point O, therefore chord AT must be the diameter of the semicircle. Any chord that passes through the center of the semicircle or the circle must be the diameter of the circle, therefore AT that passes through the center of the semicircle is the diameter of the semicircle. So AT is the diameter of the semicircle. Then we joined points D and T together by a straight line, we joined points D and A together by a straight line. In this way, we created peripheral angle ADT. This peripheral angle ADT rests on AT, that is the diameter of the semicircle, and according to rule number 5, any peripheral angle that rests on the diameter of the circle or semicircle must be equal to 90 degrees. Here we have peripheral angle AB. This peripheral angle that rests on AB, that is the diameter of this circle. Therefore, peripheral angle AB equals to 90 degrees according to this rule, rule number 5. We can implement rule number 5 in our drawing. Why? Because in our drawing we have peripheral angle ADT that rests on AT, that is the diameter of the circle. Therefore, according to rule number 5, this peripheral angle ADT equals to 90 degrees. Then we define angle ATD as alpha, we define angle DAT as beta. So in the right triangle ADT, this angle equals to 90 degrees. Therefore, the sum of the other two angles must be equal to 90 degrees. Why? Because 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. That is to say, alpha plus beta must be equal to 90 degrees. We subtracted alpha from this equation. We found out that beta equals to 90 degrees minus alpha. Then we subtracted beta from this equation. We found out that alpha equals to 90 degrees minus beta. Then we focus on the right triangle, triangle ACD. The right triangle, triangle ACD, this angle equals to beta. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees, that is the sum of the angles in any triangle. So this angle must be equal to 90 degrees minus beta, but we already found out that 90 degrees minus beta equals to alpha. So we can write here that this angle equals to alpha. Likewise, in the right triangle CDT, this angle equals to 90 degrees. This angle equals to alpha, therefore this angle must be equal to 90 degrees minus alpha. But we already found out that 90 degrees minus alpha equals to beta, therefore we can substitute 90 degrees minus alpha here by beta. Then we proved that the right triangle ACD, the right triangle ACD, is similar to the right triangle CDT. Those two right triangles are similar to each other. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So we proved that those two right angles are similar to each other according to angle similarity rule. And for the fact that those two right angles are similar to each other, we conclude that AC over CD equals to CD over CT. I repeat again, AC over CD equals to CD over CT. AC equals to capital R minus 2R, CD equals to 8, and CT equals to capital R plus 2R. So in conclusion, according to equation number 1, we found out that capital R minus 2R over 8 equals to 8 times capital R plus 2R. We cross multiply this equation number 1, we found out that 8 times 8 is 64 equals to capital R plus 2r times capital R minus 2r. But we already found out that this expression equals to capital R squared minus 4r squared. That is to say, 64, according to equation number 1, 64 equals to capital R squared minus 4r squared. But what is the value of the green shape? The value of the green shape equals to the area of the quarter circle minus the area of the small circle. Repeat again. The value of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R squared over 4. The area of the small circle equals to pi R squared. Then we took pi over 4 as a common factor, so inside the brackets we left only with capital R squared minus 4R squared. But we have already found out that capital R squared minus 4R squared equals to 64. Therefore, we can substitute capital R squared minus 4R squared here by 64. We did it, and we got that this expression in total equals to pi over 4 over 64. 64 over 4 is 16. So in total, this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers, it is equal to 50.265 square units. So in all three methods, we found out that the area of this green shape equals to either 16 pi square units, so in terms of numbers, it is equal to 50.265 square units. Okay, thank you very much.